Yeah, that was like before they cut like the percentage they take, because they were originally keep that.
Okay. Hello, everybody. Happy Monday to you. Feels like I haven't seen you for a long while. Okay, so let's continue the moisture lecture. I know you did the fat analysis already. I just want to finish moisture lecture today, I hope, and then continue with the rest of the proximate. All right. I will also send you the this week's email that I didn't send on Friday because I was out of town. So I'll do that today. Okay. All right. Let's do some recap. What does proximate analysis include? Come on. You know this? You all know this? What do we? Yes, Emma, help us out. That is one. Moisture is two. What else are we going to cover? The carbohydrate is by subtraction, but what do we also need? Ash. Very good. One more. What? Yes, thank you. All right. So moisture, ash, protein, fat, carbohydrates by difference. All right. What is the difference between moisture content and water activity? Very simple. All right, you tell me.
Moisture is just all water present in the sample, whereas water activity is the water available to be chemical and biological. Yeah.
Thank you. Yes. All right. So to repeat for the recording, moisture content, it refers to the total amount of water available or present in the sample or the food. And the water activity is that proportion of water that is available for chemical and biological reactions. Chemical reactions such as Maillard reaction, enzymatic reactions, microbial growth. Okay. What is the importance of moisture analysis? Let's just name a few. There is a whole list. Yes. Determination of stability is very important. What else? Go ahead, Alex.
Don't you need it for the nutrition label?
We do need it for nutrition label. Although we don't actually put the moisture content up in the nutrition label, we need it along with ash to calculate total carbohydrate that goes on the nutrition label. Very good. These are very important ones for nutrition labeling and for stability. And another important one is determination of standard of identity. Certain food products has a minimum and a maximum moisture content allowable, quality control, and changes in processing. So all of these are important for moisture analysis is important for. Okay, so the list is all in your slides, the whole list. Okay. So of those that we covered so far and you did in the lab, can you name a couple of moisture content methods of analysis? All right. Carl Fisher, yes. It's a titration-based method of analysis. What else? You did vacuum oven. Very good. So these are two. We did also other types of ovens like forced draft and microwave. And then we're going to talk about a few others today. Very good. What are some considerations and error you watch out for during oven drying? Or you anticipate during oven drying? William, do you want to give us an example of a potential error? I know you know. What could go wrong? Anything, huh? What's that? What could go wrong at 100 degrees Celsius in an oven? Yes, thank you. So you get burning can happen, which mostly carbohydrate. If they burn, you lose moisture, so you overestimate moisture content. Other chemical reaction, your favorite, Emma? What's your favorite? Maillard reaction. So it's a condensation reaction. So some of the bound water escapes and gets volatilized. So that's an overestimation. Lipid oxidation actually causes an underestimation because we pick up oxygen and it adds to the weight of the dry matter. So it causes underestimation. So potential splattering if you have liquid, so it's good to kind of evaporate some of that liquid in a steam bath before putting in the oven. Loss of volatiles, like flavor compounds, for example, that get volatilized, so can overestimate, and so many more that we talked about. Okay. All right, so we're going to continue with also methods that are based on drying, but they are not official methods of analysis or oven methods. So this one is infrared drying. Basically, it's a unit where infrared is used to, infrared lamp is used to heat up the sample, evaporate the water, and then you actually get directly the weight of the dry sample, weight of initial sample, weight of dry sample, and also it gives you directly the moisture content. Rapid moisture analyzer, we actually have one in George's lab, and it is quick method of analysis for moisture. Again, it heats up halogen heaters, heats up the sample, evaporate the moisture, and you can get moisture content reading based on weight difference. Distillation methods, here are a couple, the one common one is, so you put your sample plus the solvent, usually toluene. So the water, and you apply heat. So the water and solvent evaporates, go up to a condenser and get collected, condenses down and get collected in another flask. And then toluene and water are immiscible, so you can measure the water volume in that where you collected this mixture. Titration method, Carl Fisher, you did it in the lab. It is a very accurate method. It's an official method of analysis, and it's accurate mostly for dry food use, but it can be also used for wet food like cheese. It does give you good results, but it just, when you have higher moisture content food, it just takes longer to titrate and take more reagent volume. Presence of fat sometimes interferes because of the presence of iodine in the reagent, and the iodine can react with unsaturated fat. So that's possible source of error there. No heating is involved. So you have done it, so you all know what it is about. So the Carl Fisher reagent involves involves a reaction or reduction, of iodine by SO2, sulfur dioxide, in the presence of water. So the water facilitates this reaction. Solvents used are methanol and pyridine. We use methanol in the lab. So sample is extracted in methanol. And methanol is used as a blend. We correct for methanol because sometimes methanol can have some water in it as well, because hygroscopic, so it can have some water. So we correct for any potential water in methanol. And when there is excess iodine, the reaction ends when the excess iodine present is no longer reduced due to depletion of water, basically. And then we use the volume of the titrant to calculate moisture content. So we really need to get the Carl Fisher reagent equivalence, which is basically how much of that reagent reacts with water, pure water. So how much water reacts with 1 ml of KFR to be specific. So we need to determine that. As you prepare your report this week, right? Yeah. You will be doing all the calculation, the practice calculation as well, in order for you to determine moisture content using Carl Fisher. So it can be standardized with pure water or water in methanol standard, usually used. And then there's another one, sodium tetrate dehydrate. So there is an old manual one that nobody uses anymore. So we use an automated titrator that you have used, one of the common one that you've used in the lab already. Okay, that's all I have to say about Carl Fisher. There are many physical methods for determining moisture content. A lot of methods for moisture content, really. The physical methods, one is based on the dielectric properties of water. So for example, water has a dielectric constant of 80.37, and then you would just have to do standard curves and determine the dielectric constant of the water in your sample, and then convert that to moisture content. So many different methods. These specifically that are based on specific gravity are used for liquid sample. Very commonly used for milk, for example. So the hydrometer, which is you just put it in and it kind of bounces or buoyed by a force equal to the weight of the liquid displaced. So, and then that gets converted to the moisture content. And there's another one here, a special glassware that is used to compare weight of equal volumes of liquid and water. Okay. Refractive index, it's an indirect method. So we determine total solids and then you convert total solids, use that to get the moisture content. So it is based on refraction of light that we talked about earlier during the spectroscopy section, and it's correlated with the total solids in your liquid. So usually we select a specific wavelength of light, make sure it's constant, the temperature is held constant as well, and then we get a reading for refractive index that converts to total solids. Then that could be used to subtract the percentage from 100 and get the total moisture content. There are many different, this is one of the oldest, I'm sure you have used it once in your life. Who has used such equipment before where you look inside and you adjust? You never did? Ah.
The top one was used in.
Where?
Yeah.
Yeah, I thought you would have. Like, you adjust the clarity, you look inside and you get, yeah, it's a fun little unit. But then there are manual ones that are very quick as well that you would use and give you a reading. Freezing point is also commonly used for milk. It is, or liquid sample. So milk is a common one that is used to determine the freezing point that for milk is -527. So if there is more water than should be in milk, the freezing point will be high. Okay, so FDA rejects milk with freezing point above -0.507. So comparison of method, it would be good to look at table 15.5 in your textbook. It gives you a compare and contrast between different methods. It would be a good one to study from to remember the basics. All right, any questions on moisture content? Okay. So we're going to move to the other component of moisture analysis, which is water activity. Oh, you have a con. You have a con.
Necessarily. I wanted to know which one do you think is the best one to measure moisture? It all depends on the sample that you're
You
analyzing.
depend on the sample that you're analyzing. That's one, and what you have available in your lab. Every method has pros and cons, but from your exercise in the lab, you'll see that some method will be better than others based on the type of products. Yeah. Yeah, and also depending on the purpose of the analysis, you might want to do an official method of analysis versus quality control, quick methods of analysis. So no one answer. Okay. So water activity impacts the quality of the food and of course safety factors with respect to growth of microorganisms. So in terms of quality, we care a lot about spoilage microorganism as well as chemical and enzymatic reaction. In terms of safety, we care about growth of pathogenic microorganism. So this chart looks complicated, but it's actually very, very useful. And it was developed by our former late Professor Labuza, who was the icon in water activity. So at first sight, you're like, okay, what am I looking at? It's too complicated. But then it divides the fluids into three components. Dry food, for example, like snacks, like chips, powders, freeze-dried fruits, then intermediate moisture food, nutrition bars, chewy gum, honey, and so on. And then a high moist food and beverages like fresh meat, fruits, vegetable, dairy products, soft drink. And then we had tea is for when temperature is way under TG, temperature of glass transition temperature. So that temperature above that, it goes from the product goes from glassy to rubbery. That's what it means, the TG. So there are also different compartments of temperature effect as well. So here you see increase on the y-axis, increasing reaction rate. On the x-axis, it is your water activity. And then what you see here, different lines, the blue line for lipid oxidation, the brown line for Maillard browning, and then the yellow for microbial growth. So it kind of shows you at different water activity, how do the reactions, like Maillard reaction is, it starts increasing between 0.5 and 0.8, with the highest being 0.75 to 0.8 really for Maillard reaction. And then microbial growth starts increasing after 0.6 and then goes up as the water activity increases close to 1. So, and then you have products, foods that are dry food. If the water activity of, let's say, increases for potato chips, what happens to the potato chips if the water activity increases? So the relative humidity increases and the potato chips start picking up moisture. What happens to the potato chip? Soggy. So those that are supposed to be dry food, you want to prevent an increase in relative humidity because then they become soggy. You don't want that to happen. So other than physical, and then grapes, for example, they can get dehydrated. Or even if they are dehydrated, like raisins, and then you pick up moisture content, and they become softer than you want them to. So picking up moisture based on the relative humidity will impact the structure of the food, physical characteristics of the food, and also the reactions on microbial growth. So this is a perfect illustration in a figure format, I would say. And then this one, you would look at it like, oh, what am I looking at? So it's actually an isotherm structure that relates water activity to moisture content in on dry bases. Remember when we talked about how can moisture content be on dry bases? Basically, it's just the ratio of the moisture to the dry matter, to the dry solids. And sometimes your moisture content is on the y-axis and water activity is on the x-axis, just a flipped view. So what this demonstrates is really different foods and where they are in terms of their water activity. So that potato chips has really low water activity, whereas grapes have really high water activity. And then what happens, there are different levels, monolayer for different foods have different monolayer, and it's the water activity at which you have the most stability. Above the monolayer, you start have reactions and the food loses its stability over time. So here it shows what happens at 0.6. You start having microbial growth. And then if it's potato chips at 0.35 to 4.45, you lose crispiness and so on. So, and this kind of takes some of those examples and put them out in bullet points for you. So most monolayer values are between 0.2 to 0.3 for foods. So they are most stable, at which point you lose crispiness upon water gain, 0.35 to 0.4. And then between 0.3 and 0.4, you get stickiness for sugary powder, and you gain moisture, and then the sugar with the moisture gives you that sticky feeling. And then 0.55, hardening of soft material upon water loss, like raisins, marshmallows. If they lose water under their 0.55, then they become hard. That's why sometimes marshmallow, if you open the bag and leave it, it will just harden over time. And so on, growth of microorganisms, onset 0.6, 0.7 to 0.8, maxima and chemical reactions like the Maillard reaction, and 0.85, onset of bacterial pathogen growth. And then above that, we get rapid microsporage. Did you cover that in food chemistry? Kinda? Yeah. Okay. This is just a reminder. And also here we talk about measurements of the water activity. So the principle of measuring water activity is measuring this moisture at equilibrium that is above the food. So in the head space above your food product or beverage. So we use relative humidity sensor to measure relative humidity at equilibrium. Basically, that's ERH, which is relative humidity at equilibrium. So, and we always have to control, when we're measuring water activity, we need to control the amount of sample, the time that you leave the sample to equilibrate, the temperature, and also we need to calibrate the sensor. So there are different methods for measuring water activity, and you have used decagon device, correct, in lab. It's very simple. You don't do much, but it's measuring the dew point. And this is a direct measurement. After you reach an equilibrium, you measure the water activity or the relative humidity at equilibrium. This is detail in the table 15.8. And there are two ways of measuring, common ways of measuring water activity, either dew point, like we did in the lab, or electric hygrometer. But basically, we're just measuring relative humidity at equilibrium in the head space above the sample. This table here shows you the water activity, FYI, for different fluids. So if we look at honey, for example, it has a water activity of 0.56, right? Yep. So of course, you don't have to memorize any of that. It's just FYI. And this table actually is really good as it tells you different methods and when they are used. The direct method, the indirect method, and then the water activities. In case you want to give an example. So very briefly, I'll go over moisture sorption isotherm. It used to be a method that we actually plot, or we used to do water activity and moisture content and plot the isotherm to determine the monolayer of different food products. So in the past, what we used to do is actually take baby cereal and put it in desiccators at different saturated salts. So what we used to do is do 0.11 water activity, 0.32, 0.4, whatever, and then all the way up to 0.8. So we get about 7 different salt solution, 7 different relative humidities, and store baby cereal in Petri dishes and let them equilibrate for about 3 weeks before the lab. And then when the students come, what they used to do is every group would take a sample at a particular water activity that has been stored for 3 weeks at that desiccator under that specific saturated salt for that particular water activity, and measure water activity using the decagon, and measure moisture content using Carl Fisher. So every group would do that, and then we will get those different water activity and moisture content at different relative humidities, and then plot an isotherm. An isotherm is basically a relationship between water activity and moisture content. So moisture content on the y-axis and water activity on the x-axis. And then we get graphs. And then we have 3 different ways of calculating or plotting these graphs, but the most common one that gives you the most accurate reading across wide variety of food is the DAB isotherm plot. And this came from 1 year where we did plot for baby cereal. And then we determined empirically the monolayer and how it and extrapolated the water activity at that monolayer. So the desiccator method is what I determined. I was just explained it for you. And then there is, during that method, you actually measure the water activity at different relative humidity because there is the sorption and desorption. So sorption is just picking up water, and desorption is the losing of water. basically, and that is your plot. But here, instead of water activity, it's relative humidity, but you can plot water activity. And then there is an instrument that gives you the moisture absorption isotherm without having to use desiccator. You would just put the sample in and the sample get equilibrated at different moisture, relative humidities, and you get the water activity directly. And then the instrument itself plots the isotherm for you. And that is that. Questions? I didn't expect to finish that fast, but I have another lecture ready for you. Go. Ash content. It's very easy. Ah. You're awfully quiet today. Is it because it's Monday? Yeah. All right. So the ash content is pretty low key. All right. What's the definition of ash? When you hear the word ash, what does it mean to you?
Solid,
Huh?
the solid,
Solid?
the solids in
The solids in food?
powder.
In powder.
Inorganic.
Yes, it's inorganic. It's solid. Yeah. Okay, so it is really the inorganic matter. How do we get to the inorganic matter? Huh? One time I was, many years ago, I was bored. So,
That was the last.
no, I get bored quite often. But when I was putting together this lecture, I was like, okay. So, you burn the food at really high temperature. So what happens to the organic matter? It just escapes. Here's the organic matter running off. And then the inorganic matter remains. So the ash is the inorganic matter, and it is mostly your minerals. Okay. Unless you have contaminants like soil in your sample or any other inorganic matter that ended up in your food other than minerals, which we don't want. What is the importance of ash analysis? What did you tell me, Ali, about the importance of moisture analysis?
Nutrition labels.
There you go. It's part of approximate analysis for nutrition label. We need it so that we can calculate total carbohydrate. So it's not anywhere on the label in terms of an actual mass. Of course, there are minerals on the label like sodium, potassium, calcium, iron, but the total ash content is not on the label. Why is it important to ash your sample as well? So to calculate total ash, and what else? What lab did you do? Huh? Before the moisture, what did we do? Which lab you actually started with ash? Atomic absorption. So we need to ash the sample for us to determine certain minerals. Who knows Popeye? Do you remember? Yeah, do you know the song? Popeye the Sailor Man. Toot toot. Huh? All right. So I used to get strong by when eating spinach, which is high in iron. So anyway, so it's important for us to determine ash content because we need to determine the minerals that they go on the label: iron, calcium, potassium, and sodium. These go on the label, but sometimes also if we fortify with certain mineral, we do have to put that on the label. Other than these four. So sample preparation, the first thing we have to do for high moisture food is dry. Why is that? Why do we have, remember in ashing, I don't know if we said it already, you put the sample in something we call muffle furnace oven, very high temperature, minimum of 450 degrees C, 550, that's the average. So what happens if the moisture in your sample is high and you put the sample at this high temperature? Splat. So the moisture wants to go off or evaporate very quickly out of your sample. So if you have cheese, for example, it's just gonna bubble off and you will lose parts of that cheese outside of that crucible. So in lab on Wednesday, you're going to do ashing. So group C will be doing cheddar cheese that has been pre-dried for you. So cheese has high moisture content, whereas almond and baby cereal, the samples will be ashed as is. No need for drying. Milling and grinding. So it's very important that we mill the sample or grind the sample so you have a uniform particle size, and so that when you want to take out the sample, you take it out from a homogeneous sample. So your cheese for group C will be pre-dried and milled, or you will mill it in the lab, one or the other, and then you will weigh out your milled sample into your crucibles. The almond you would mill in the lab. You milled the almond, right? Group A? Or was it milled for you? Huh? You did? Yeah, okay. Who's group A? Yeah, you remember milling it? You don't?
No, they.
You milled it for them. Okay. Lucky. All right, so, but when we mill or grind the sample, we have to be cautious about potential contamination. Like if you're using a coffee grinder or any other grinder, if it's made of metal and some of that metal ends up in your sample, you could overestimate ash content. And depending on what metal you are trying to measure, if you're doing atomic absorption, if there is iron in your bowl that you use to mill, you might have overestimation of iron. So we have to be really careful to avoid using any mill or grinding tool that would result in contamination. Fat extraction, sometimes we do that in case the fat is really high because it can cause smoking and potentially also splattering in the muffle furnace. Also, again, group C, you will be putting your crucibles with the cheese on a hot plate to smoke off those fat so that you avoid splattering in the high temperature muffle. Sugar products could cause foaming, plant material, meat, because they're high in moisture, they will cause splattering. So there are certain precautions depending on the type of sample. basically reduce the water content and reduce the chances of foaming and smoking and burning. So there are two most common methods for ashing: dry ashing and wet ashing, and there's microwave ashing that could be also dry or wet. So dry ashing is just putting your sample at high temperature, and then all the organic matter combusts, burn off, combusts. And then you're left with the inorganic matter. Wet ashing is you don't put at really high temperature in a muffle furnace, you use corrosive concentrated acids. And then you do some heat, but not very high heat like the muffle furnace. So the acid and the heat oxidizes organic matter and they come off as gases, CO2, SO2, and O2, H2O. And then what is left in the acid are your dissolved minerals. If you remember when you did the atomic absorption, in order to dissolve the minerals, what did you add to your crucible? What is the first thing you did to the ash in your crucible? HCl. You added concentrated acid to bring those minerals in solution. In wet ashing, the acid used will solubilize your mineral. So, but one thing I would say, and I would always ask it at some point, is wet ashing is not used for proximate analysis. Meaning, you won't get a weight of ash. You cannot get a percent ash. You get your minerals dissolved in the acid, but there is no value that you're going to obtain on the balance. You know how you came the next day to get the moisture pans weighed? The same with dry ashing. You're going to combust the sample and you're going to come the next day and weigh the amount of ash left in your crucible to get percent ash. And that percent ash is used in this 100 minus everything to get the total carbohydrate. With wet ashing, there is no percent ash you're going to get. This is used to actually for mineral analysis. You wet ash, and then you determine minerals in that acid solution. Okay, let's talk about dry ashing. Dry ashing is, like I said, you use a muffle furnace. You'll see it in lab this week on Wednesday. You're obviously not going to put in your crucibles while it's hot because it's really high temperature. So you would weigh your sample, write down the weight, and then you put them in an oven that is placed under an exhaust where the fumes are sucked out and not really in the room. They don't go in the room. So you'll see that in lab 65 in the basement of the Food Science and Nutrition lab. So you will put your samples in that muffle furnace, then you turn it on to anywhere between 450 and 550 degrees Celsius. There are different sizes of the muffle furnace. They come in so many different sizes. The one that we have in 65 is the larger one. There is one in room 155 as well. That is a smaller one. So at high temperature, there is combustion or incineration or burning off of your organic matter. And then you're left off with the ash. So you get to choose different types. You have different types of crucibles. So here, so the different types of crucibles, you get quartz, which is the most expensive and very durable for acid food and very durable at high temperature. Not so much durable for alkaline food. Porcelain, however, is cheap, durable for high acid, can be durable for a high temperature as well, but it can crack, like break, when temperature changes very abruptly. So that's why when we put the samples in and we turn on the heat, the temperature goes up gradually. Then we turn off the heat, leave your crucibles inside until temperature goes down. Then we take them out and put them in desiccators for you to cool down. Otherwise, those porcelain crucibles will crack. And given that they are cheap and you can go around not having them crack, they're used very often, and these are the ones that you will be using in the lab, which you already used for atomic absorption. Platinum is the best in terms of heat durability, acid, alkaline, but it's very expensive, not used when you really have a lot of samples to process. Steel is not as much preferred, especially that it contains iron, nickel, chromium, contamination of these minerals. Quartz fiber, this, basically it's disposable, has pores, so good transfer of heat, and also durable. Some people use those as well. But most commonly, again, it's porcelain. All right, I'm going to stop here so that we can continue with this slide when we get to it on Wednesday. All right, we'll see you Wednesday. Take care.